Our subject for today is warp drives, the entire general concept, not just the version discussed by Miguel Alcubierre. Truth be told, unless you've really dug into the heavy math end of it, discussion of the Alcubierre drive normally are just discussing warp drives in general. Now, as is going to be a habit in this series, we also have a general subject of physics we'll be talking about as well, only in this case it's going to be 4 of them, and it means we'll be spending more time on them than the warp drive, but they are key to understanding it. To talk about warp drives, we need to talk a bit about general relativity, which we're going to need for the next episode on wormholes too. We also need to talk about mass, specifically negative mass, but also in general the way mass actually has multiple traits that might not be entirely connected, like how it interacts with gravity and inertia. We also need to take a look at the notion of why warp drives, in spite of getting you from point A to point B faster than light normally would, don't actually violate the rules. And in that respect, we also need to explain how distant galaxies can travel away from us faster than the speed of light without doing so themselves. And lastly, we need to talk about the Unruh effect, which is very like Hawking radiation but for event horizons caused by objects accelerating very fast. Now, if you've already got a good familiarity with the Alcubierre drive from reading pop-sci articles about it, you've probably heard this term and negative mass as well. But those don't generally go into much detail, and that detail is what this channel is all about. But the basic concept of a warp drive is actually very straightforward, and you are probably already familiar with it. By various proposed means, typically by using negative mass or energy as part of the process, a ship creates a bubble around itself where in front of it space has gotten all crunched together and shrunk down, and behind it space has gotten all expanded. It warps spacetime in front and behind it, and this shoves the bubble of normal spacetime between them forward, and at speeds not constrained by the speed of light. Nothing can move through spacetime faster than light, except spacetime itself, which is exempt from this, and it carries the ship along. This is very handy, since it not only allows you to go faster than light, but to jump up and down from those effective speeds without turning your crew into messy pancakes. You don't need inertial dampeners in a warp bubble because there's no change in inertia to dampen. And physics tells us that if certain things turn out to be true, it is actually possible we might be able to build one of these things one day. And while they do have a maximum speed limit, the last calculations on this I've seen for that maximum let you jump between galaxies on timescales so short you need an atomic clock to measure them. The faster you want to go, the harder, but fundamentally, the warp drive lets you travel the galaxy quickly, and could even eventually be refined to let you cross the whole universe even, in very short times. It will probably turn out to be impossible, but we can't rule it out just yet. That's all you really need to know about the warp drive, and if that satisfies, hey, great, thanks for watching. From this point on, we'll be digging into the guts of how it works. Now, this concept is rightly associated to Miguel Alcubierre, since he took the concept and changed it from a seemingly impossible concept into, well, an almost certainly impossible concept. And his 1994 paper on it, which is linked in the video description, reignited a lot of interest in the concept, both from the public and scientists too. But the concept does predate him, in myriad forms, of either contracting space in front of you using mass, or somehow actually creating or deleting space behind or in front of you, of warping space-time in order to get around the speed of light. Unfortunately, most of these ideas are either flat out impossible, or relied on using something we're not even sure exists, or actually pretty sure does not exist. And that remains the case today. But a lot of folks with genuine credentials to be looking at the subject have made a lot of new improvements on it, but they also found a lot of new problems with it too, now that we're giving it a serious look. The 2 key ones are getting your hands on negative mass, and getting burned to a crisp inside the bubble. But before we discuss either of those, let's do a quick overrun of general relativity, and I mean quick. General relativity was a follow-up on special relativity done by Einstein to deal with the concept of acceleration, what's going on when you're actually speeding up or slowing down. Now, back in episode 1, we did a 3-minute review of special relativity, and I pointed out there that it was based on 2 core assumptions. The first being that the speed of light was constant in all inertial frames, and the second being that physical laws basically work the same anywhere and at any speed. The problem is that an inertial frame of reference is just a complex way of saying that something is moving at a constant speed, which to them seems like 0 speed. You can't tell when you're moving at constant speed, and the only reason you think you can is because if you're zipping down a highway, you notice all the interactions of the wheels on pavement, or cars slamming through air that are moving at different speeds relative to you. So I can say my speed is 0, and everything else is moving relative to me, to my inertial frame, and all the math and physics works just fine. Unless you're accelerating, changing your speed, changing your inertial reference frame. Then you get problems. Problems patched up by general relativity. What Einstein realized was that acceleration and gravity are fundamentally the same thing, or at least cannot be torn apart. Now unfortunately the classic example of this, a guy standing in an elevator or a box being accelerated, actually does let you tell the difference between the two, but let's look at that example anyway. If I'm sitting in an elevator that doesn't let me see outside, that's inside a vacuum tube, I have no way of knowing if I'm moving or not, but I can definitely tell which way is up or down, and I can tell if the box is accelerating. But I actually couldn't tell if that up and down feeling was from gravity or from acceleration. This isn't quite true, since gravity generated by roughly spherical objects noticeably weakens as you get further from the source. So if I have very sensitive equipment, I can measure the force of gravity at my feet and at my head and find a slight difference. This difference is a lot more than slight around very dense and massive objects like black holes, and that difference is what rips you to pieces. It's also what rips virtual particle pairs apart to generate Hawking radiation, as we discussed in the video on that, though today we'll see another version of that with the Unruh effect. But the key thing is you can't tell the difference between gravity and acceleration except in terms of traits specific to how it's being generated. I would know I was accelerating, for instance, if I could feel a giant rocket motor throwing underneath me too. Or if I cut a hole in the wall and looked outside. That's all incidental. Now if I take a little laser, hang it on the wall, and level it with the floor so it should be hitting the exact same height on the other side of the elevator, something strange happens if I'm feeling gravity or acceleration. The beam will hit just a little bit lower, and much lower the more acceleration or gravity I'm under. That's not surprising with acceleration. The box has moved since photons came out of the laser, and even though normally that motion wouldn't matter since the laser had that same motion, by accelerating you've actually got the box moving faster when the photons hit the other wall than when they left the laser. The path of the laser will seem to be bent, though of course we know that it isn't, and it's just because the elevator moved relative to when those photons came out. Except we see this exact same effect from gravity, and the box didn't move at all. It's identical. While the force acting on you and the box and the laser is from gravity or acceleration by a rocket, the bending of that light beam will be the same for the same force. More force, more bending. So gravity and acceleration seem to be the same thing, and that is general relativity. That's the basic premise of general relativity anyway. The result of it is that space and time can be warped by gravity, which means they can be warped by mass, and since mass is a type of energy, E equals mc squared, it can also be warped by energy. That's one trait of mass, but there's actually three more of some interest to us today. Mass is also a thing that resists changes of inertia, but it's also a thing which controls how much an object is affected by gravity, or affects other things with its own gravity. And that's actually a bit weird. I mean, we've got four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. But while an object's electric charge controls how strong the electrostatic force it pushes or pulls on things with is, it's still its mass that controls how the object's inertia is affected. Also weird, as you probably know, is that these three other forces have a positive and negative value, but mass and gravity only seem to have positive and attractive aspects. So it's not surprising we kick around the notion of negative mass, or a repulsive gravity, anti-gravity. But negative in what respect? I just listed three traits it has: how it resists changes of inertia and how it emits or responds to gravity. Negative in all three, or just one or two? Could it be possible, for instance, to make something's inertial mass negative only, or even just much lower, so that a shove sends it flying away far faster than we'd expect? Or for negative inertial mass, sends it flying towards us when we push it, instead of the other way around? On the same note, could we make an object respond more weakly to gravity, so we could lift very massive objects with ease, or build massive buildings more easily? Or even make this negative so we can shove a ship off a planet's gravity field instead of being pulled by it? Or for active gravity, the aspect which pulls on stuff, could we make this repulsive instead to shove everything away from that object, or increase it to generate artificial gravity? Pretty interesting stuff. And lowering inertial mass is sadly underused in science fiction, since it not only solves the energy problem for making things go fast, but also has the unintended consequence that spaceships that can go fast have access to enough energy to smash worlds. Generally speaking, sci-fi stories don't want the Millennium Falcon to be able to blow up planets. If you can just lower something's inertial mass to a tiny fraction of normal, a regular old rocket engine would speed you up to relativistic speeds, and when you turn the effect off, it would stop like a brick, dropping to its natural speed from that rocket acceleration, or even lower if you could go the other way around too and increase inertial mass. And the passive and active gravitational aspects of mass give you similar tricks. One for active gravitational mass is letting you ramp that up, not just for handy artificial gravity on ships or space stations, but to warp space like a massive body does. And the reverse effect would let you expand space. So negative mass, regardless of its specific properties in terms of these traits, would be very useful stuff regardless of its FTL options. But that's the one that interests us for the warp drive, because if you warp space enough, in front and behind you, expanding behind and contracting in front, you will start moving along. Do it enough and you will move faster than light. Now this, in and of itself, isn't a problem. Nothing can move through space-time faster than the speed of light, except space-time itself, and it can carry stuff along, like galaxies. The effect of an expanding universe, usually attributed to dark energy these days, is that stuff is moving ever farther apart and actually accelerating away from each other. And if you go far enough away, you can't see each other anymore because you are moving away faster than the light can catch up. That's not a problem for relativity. The notion that tiny pockets of space are constantly popping into existence everywhere, probably in little Planck volume units that are as small compared to an atom as an atom is to a solar system, is certainly a strange thing. And you probably have tons of these little new bits of space popping in you all the time. But it doesn't matter because local forces easily keep everything glued together. But over intergalactic distances, the forces binding everything together, which is basically just gravity at that point, already the weakest and freakishly weakest force in the universe, just can't keep everything bound together with all the huge amounts of new space popping out of nowhere. Over long enough distances, this can result in truly immense apparent speeds between galaxies, and light can't cover the gap because new space is popping up between these places that it has to travel through too, and at such a fast rate it will never reach us. So effectively, every galaxy is an FTL spaceship from the perspective of some other galaxies, actually most of them, though of course they can't see us or us them, and this has some effects, specifically the Unruh effect in terms of event horizons, which we'll get to momentarily. Warp drives fundamentally operate on this same principle. There are some variations in style, but generally they work by either crunching up and expanding space-time, or by outright deleting chunks of it and adding them in behind. This gets around the FTL problem the same way the cosmic expansion we just discussed does too, and it's why dark energy gets a lot of looks, since that's the force currently assumed to drive it. Of course, we don't really know how much energy it takes to make a new piece of space, since theory and evidence on vacuum energy slightly mismatch. Well, slightly is probably an understatement. The difference is like 100 orders of magnitude, which is sort of like the difference between a grain of sand and a galaxy, except bigger, and this has been dubbed the vacuum catastrophe, as well as the worst theoretical prediction in the history of physics. Still, at a strictly theoretical level, it ought to be possible to artificially create or delete chunks of space. The former happens constantly after all, and we can certainly contract space. Gravity does that all the time. I mean, you're doing it just sitting there. And if negative mass or energy exists, we can expand it too. And while we don't have a shred of evidence indicating negative mass does exist, we do have a bit better indications that negative energy does. So the ability to contract and expand space, and thus do a warp bubble, does seem like it might really be on the table. If so, you ought to be able to do a warp drive. And while the Alcubierre drive and other early versions of this tended to require an amount of negative mass, on par with large planets or even more, newer calculations have indicated we might be able to do it with even just 1,000 or so pounds of it. But on this channel, we've never flinched away from building truly huge objects, often ones much larger than a planet, so even those higher end values shouldn't be considered prohibitive. So if we've got a warp bubble, all is well, and there's good reason to think it might be possible, except for two problems. As I said, Alcubierre's 1994 paper inspired a lot of other deeper looks into the idea, and just as the paper is linked below in the video description, so is one by Finazzi from 2009. He noted one problem, having to deal with the bubble destabilizing when he looked at the renormalized stress-energy tensor, but we can't really discuss anything involving the word tensor on this channel without devoting many hours to going through complex math. He also pointed out another problem that will exist for warp drives. And that's the problem that once you hit FTL speeds, you will end up with a white hole in front of you, a topic we'll discuss another time and has plenty of its own problems, and a black hole behind you, and both will just follow along with you. Now that's a topic we did discuss a lot before, in the video on micro black holes, virtual particles, and Hawking radiation. And here we get a similar sort of effect. Black hole event horizons are caused by gravity, but as has been mentioned, gravity and acceleration act a lot alike. So it's probably no surprise that acceleration can also cause an event horizon. And an event horizon is just any place that you can't see events on the other side of. For a black hole, that's where nothing occurring on the other side can get light out to show you what's going on. This same thing can occur with accelerating objects. Normally, no matter how fast you're going, light will catch up to you, But if you're constantly accelerating, it's a bit of a different story, and more to the point, if you are traveling faster than the speed of light, when you look out the back of your ship, you won't see stars flying past. You'll see nothing. Black, empty space, because the light they're emitting can't catch up to you anymore. Even before you get to the speed of light, those particles will redshift down into near invisibility as you get faster and faster. They do reverse in front of you, blue shifting so much they also become invisible, as they blue shift to ultraviolet, then X-ray, then gamma, which is a bit of a problem itself. But behind you, there is an event horizon. You can't see or hear anything behind your ship. Okay, so what? That's inconvenient, but not really a problem, right? Well, no. This is where the Unruh effect comes in. The concept is that a vacuum depends on the observer, like so many other things do. Now this requires a quick caveat. In physics, a vacuum isn't quite the same as empty space, something that doesn't really exist anyway, but rather as a place where everything is in the lowest possible energy states. You can think of that as meaning very cold. If you're accelerating and you look at it, it won't seem quite as cold. For 1 g of acceleration, the same as normal Earth gravity, this isn't much warmer, about a billionth of a trillionth of a degree. But if you're accelerating fast enough, it can be a lot hotter, and hot things give off black body radiation. And again, a vacuum in physics isn't empty. In fact, it's full of a lot of stuff like virtual particles. Now, acceleration and gravity are basically the same thing, so it shouldn't surprise you that this effect looks basically identical to Hawking radiation that we looked at before. And in fact, it's often just called Hawking Unruh radiation, and you can use Unruh effects to look at the event horizon of a black hole and get the same results. Well, the flip side applies too, and that event horizon trailing your ship doesn't just look like a black hole. It basically really is one, complete with Hawking radiation. And a whole lot of it too once you hit FTL speeds. Finazzi calculated an effective temperature for this event horizon pretty close to Planck temperature. And while those of you familiar with Planck distance and Planck time are used to thinking of Planck units as ridiculously small, Planck temperature is the exact opposite, and usually consider the opposite of absolute zero, or absolute cold, as being absolute hot. The hottest something can be before physical laws simply break down. So this black hole trailing our ship is burning at temperatures that make the core of the largest, hottest stars look like winter in Antarctica. So you'd be burned to a crisp. I'd like to spend more time on Unruh radiation, but it's not something everyone agrees actually exists, and it's also hard to give a proper visualization for where the energy being emitted is coming from. I suppose, for those of you who saw the Hawking radiation video and remember my explanation in terms of virtual particles, it would probably be decently accurate to think of it in those terms. There we said that right over the surface of an event horizon, same as everywhere else in the universe, virtual particles are constantly popping up in pairs and usually annihilating with each other almost instantly. But every so often one ends up on the other side of an event horizon before this can happen, and the other sails off as a now real particle with real radiation. On small black holes in particular, this is very powerful because right over that event horizon, the change in gravitational force from even a very tiny extra distance can be monstrous, and rip the virtual particle pair apart as the one slightly closer gets yanked away. Here you could think of it in similar terms, since gravity and acceleration are, again, pretty much the same thing. If that event horizon rolling behind you is separating virtual particle pairs before they can reunite and mutually annihilate, then the ones on your side of that horizon are acting just like the escaping Hawking radiation of a black hole. Either way, while the Unruh effect is debated, and we've never actually seen Hawking radiation either, the same physical models that are letting the warp drive work strongly indicate the interior of that warp bubble is getting blasted with huge amounts of Hawking radiation, or its equivalent. Now if we can get around that, or it's wrong, if we can keep the field stable, and if negative mass exists, there's still two more problems with the concept. First is that you're probably collecting an awful lot of energy at the front of the ship, and some feel that when the ship decelerates, that energy is going to slam forward and hit your destination with planet-destroying forces. I don't consider that a problem really. Don't aim your ship exactly at your final destination. And as we discussed in the past, even a regular old sublight ship traveling at relativistic speeds can just jettison some of its garbage before slowing down and expect it to whack the planet ahead of it like a bunch of nuclear bombs. Plus it makes a handy weapon, and an FTL one. So while it's a concern, it has nothing to do with the functionality of the concept, and just about every technology brings in new concerns for destructive use. The second and last one for today is only applicable to certain versions of the warp drive, but brings up an interesting point in terms of the Fermi paradox, which we spend a lot of time discussing on this channel. There's a concern where you need to pre-place matter along the path to get this warp effect to work at all, sort of like a railroad track. Now that's fine in and of itself. It's great for the Fermi paradox too, since as I discussed in the Dyson dilemma and the compendium, the Fermi paradox is a whole lot worse when you bring FTL into things, but if you have to make the first trip at slower than light speeds to allow you to get there and back in the future at FTL speeds, it isn't really a problem for the Fermi paradox. Aliens can't just pop across intergalactic distances without building the track first. But it does limit the utility of the warp drive, since it means you have to get to a new destination the first time the hard way, and we'll see this again when discussing wormholes in the case where you have to make the opening and exit next to each other, and then tow them to their final destination at sublight speeds. But that still makes it very useful. The problem is that in some analysis of this, the only way to properly pre-place these masses actually requires you have a working FTL drive to begin with, and if that turns out to be true, you have a catch-22. You can't make an FTL highway without already having a FTL highway there. Of course, the idea of using regular ord mass, or preferably dark matter if you can find a way to manipulate it, in big long conduits that would contract space around them and let you send things along them seemingly faster as a sort of pseudo-FTL highway or telegraph, is nothing new either, and something we'll look at more in the future too. And they also have the issue that you have to go there the long way the first time, but without any catch-22. So, if we can come up with negative mass, if we don't need whole planets worth of it, if it turns out we can keep the field stable and either there is no Hawking Unruh radiation burning you, or we can find some way to shield us from it, and if you can build one without needing to pre-position mass, or at least without needing an FTL ship to pre-position it, then we finally do have a working faster-than-light ship. And the good news is, NASA is doing some basic proof of concept of the idea. Articles you've seen on this tend to overhype that a lot and view it way too optimistically, but it is being done, and promises some interesting new data regardless of the outcome. So that's the warp drive. So far our best candidate for FTL. Next time we'll look at another, more familiar FTL system when we look at wormholes, which we'll see also need negative mass to work, and will bring us back to look at the time travel problems we saw last time. That video will be a little while, as we take an initial look at transhumanism technologies and concepts next week, and then a trip back to the Fermi paradox for a look at the simulation hypothesis, the notion that we might be living inside a giant computer simulation. After that, we have a number of subjects in the queue that might come before or after the wormhole video, but it will probably be at least 3 to 6 weeks before we get there. If you want alerts when those videos come out, make sure to subscribe to the channel, and if you enjoyed the video, hit the like button and share it with others. As always, questions and comments are welcome, and feel free to try out some of these other video playlists. Thanks for watching, and have a great day.